Okay, so we are talking about the linear model, and let us summarize the linear model for classification. We have worked on the perceptron learning algorithm before, and right now what we are looking at is the linear classification model, which is nothing but the perceptron. So let us look at it from the lens of all the theory that we have developed until now, right? So let's revisit it. And what is linear classification? Well, we are trying to classify the outcome in like two or more classes essentially, right? So therefore, for the linear classification hypothesis set, we can write down that this set looks something like this. So h of x equals sine transpose x. We already know this, but I'm just like, as I said, revisiting where my w essentially belongs to the d plus 1 dimensions. If you remember why d plus 1, because of the added bias in there. And in addition to like defining the hypothesis set, we also proved or sort of discussed that for the perceptron, the VC dimension of the perceptron was d plus 1, which is really good. So it is one of the good hypothesis sets. And therefore, we could establish the very first principle of learning, the very first rule, which links E out to E in. And this was, why was it good? It was good because like the error bar was of the order, like roughly speaking, it's of the order square root d times log of n over n. Now notice I've replaced the VC dimension with d because like one is like constant, so it's almost d times log of n over n. Okay, so this is like the first step of learning that is accomplished by the perceptron, and the VC dimension is known, so this is something that we can come up with. What is that second step of learning that we are interested in? So the second step of learning, if you remember, was to get E in as small as possible or as close to 0 as possible. And we have the perceptron learning algorithm, PLA, that we need to use in order to accomplish that. So my PLA is going to accomplish that. Okay. Now, if the data is linearly separable, then all of that is good because eventually we will come up with a G that would be like actually equal to 0 in most of the cases, right? So we will come up with that. And so there is a theorem also that we looked at, and PLA will accomplish this if there is linear, like if the data is linearly separable. So the second step will also be accomplished. So the first step and the second step both accomplished by PLA. Now, what happens if the data is not linearly separable? And the question that arises is, what happens if data is not linearly separable? That's the first question. The second question is, in that situation, can we or how can we ensure the second step of learning, which is E in whatever G we come up with, almost equal to 0, or E in being like very small, right? So how can we accomplish these two things? Now, the answer to question 1, let me write it, this is question 1, this is question 2. So the answer to question 1 is that I can update the perceptron learning algorithm to tolerate some kind of error. So what if this tolerates some error? So tolerate some error, maybe not come really equal to 0, but if I'm allowing some kind of an error, then I can ensure some level of E in, right, which becomes small. And this tolerance of error is known as the pocket algorithm that we are going to look at today. So the answer to the first question is we can come up with some error tolerance, and that's known as pocket algorithm. For the second one, can we ensure E in equal to 0, which we usually achieve when the data is linearly separable? Well, if we look at the problem itself, right, it is a very hard combinatorial problem. Well, believe it or not, it's a very difficult problem to solve. It almost cannot be solved, right? So we cannot ensure, in short, we cannot ensure E in be exactly equal to 0 when the data is not linearly separable. So what should we do? Now here comes the machine learning expert or the domain expert, and both of us, they sit down And one solution that they can come up with is a good feature set. And we'll just see in today's lecture how that is going to help us. So what they have to come up with to answer the second question is to come up with a good feature set. If we are able to accomplish that, then to a certain degree, we can ensure En to be small. Okay, so how does that work? So first of all, let us look at what is like non-separable data and how pocket algorithm works, right? So this is my non-separable data. This is an example of non-separable data. So no matter what you do, you cannot classify all the points correctly or all the points on the right side of the hyperplane, right? So that's what linearly non-separable data means. And so the way the PLA algorithm, the perceptron learning algorithm was working was that I had some weight at some iteration t, and I was adding the y star and x star to it so that it ensured that my my separator or my line moved in the correct direction or in the right direction. And this led to the next iteration. Right, this was the basic idea behind the perceptron learning algorithm. Now, in the perceptron learning algorithm, if we want to answer the first question here, what happens if data is not linearly separable, we wanted to allow some error tolerance. So one way of doing that is by using the pocket algorithm. And the way the pocket algorithm is going to work is I'm going to get the weights. So whatever weights I got here, right? Let's say this is some W, I don't know, WT already is there. Let's say WL, right? So I got this. And so using this, I'm going to calculate my En at this point, right? At this iteration, I'm going to calculate En. Now, if this is the best En I have encountered, if this is the best En I've encountered, I will put that in my pocket. That's why it's known as the pocket algorithm. So the update of PLA is the pocket algorithm, and this is how it works. Keep putting the best one in your pocket. So what happens, like in the next iteration, let's say if the new set of weights are better than the ones that are already there in your pocket, then just like go and update that. And if not, then just like keep whatever you had until you stumble upon a better one. That's what we do, right? So keep updating, throwing away the earlier ones if we find a better one, essentially. So as you can tell, so this is a slight update to my PLA, because I'm just like keeping track of En. And of course, like depending on the size of the data and other things, depending on the dimensionality of the data, of course, it seems like an expensive process, right? So first of all, first point to note is that minimizing En is a hard combinatorial problem, right? The pocket algorithm works like this: run PLA at each step, get the best, right, so far. And believe it or not, it works really well. But as I said, it's a costly process, and it works if you're able to tolerate some error, and then it gives a reasonable result. A few things to kind of remember is that every new set of weights in your pocket are guaranteed to get better as you move on, obviously, because that's how you're keeping track of your En, right? And you have to also take care of the stopping criteria, because you're not really optimizing anything here. You are iteratively getting a better sort of solution. And so you have to decide when to stop. So the stopping criteria is usually like, in most practical situations, it's like 1,000 to 10,000 iterations, depending on what kind of problem we have. Sorry, iterations. Yeah, not iterating, right? So it depends on the dimensionality of the data, as I said, and the size of the data set, because like at every step, what we are updating is this W, right? And so this W is like proportional to the dimensionality, obviously. And then you have as many observations. So you have like those many data points. So En has to be computed for that. And so obviously we can also improve. So there are certain ways of like improving on getting a good En, getting a good result. There are ways. For example, one of the ways is to get a starting point depending on whatever domain knowledge we have. So get a better starting point. Get a better starting point is one way of getting a good result. So get a better starting point, depending on your domain knowledge, of course. That could be one. And then there are algorithms to get good starting points. So this is the first one. The second one is there are algorithms that are available to get a good starting point for my PLA, which is now my pocket algorithm. So basically, my pocket algorithm will help us get some result such that we have some error tolerance and we can get a reasonable like E in, right? So let us try to kind of see how we can get like, obviously this cannot ensure the best E in, right? Because again, we are not optimizing over the entire problem. But of course, we can get a reasonable one. And let's look at this pocket algorithm into action with an actual data set. So let's look at this digits data set. Okay, the moment you look at it, you know this is the famous handwriting recognition problem, and that's where the digit data came from. It's a 16 by 16 grayscale image, like every point in the data set is a 16 by 16 grayscale image. And I know you've already seen this before, and I'm sure you've solved problems using this. And so you might be a little disappointed why we are like, again, looking at it, might have looked at some other unknown problem or a new problem. Well, idea being, and also because the textbook uses it, and so that's why I'm using it. So idea is that we wanted to illustrate all the theory that we've learned on this standard, well-known problem. And the good thing about this is that you can, for most part, test most of the theory that we have built on this. So it's good for illustration, and obviously it has been there for quite some time. And just to give you an idea that we are not concerned about the pre-processing part of this data, like how it was collected. So that's the pre-processing part. I'm not going into the details of that. So basically, there are some already existing computer vision algorithms that get the hand written. I think it's from the US postal data that they get these handwritten digits, and then they focus on like the way they kind of come up with these data points is that they focus on certain aspects of how the digit was written. For example, whether it was vertical versus like within a square, how much fill each like digit achieved and so on. So there's some kind of scaling and other things involved. Rotation is also involved. And eventually the input is normalized such that it becomes suitable for our machine learning usage, machine learning models. So there is some pre-processing done. I agree. We are not jumping into that. We are using that pre-processed data. And actually that is the convention for most machine learning problems. So we are taking it from there. Okay, so having said that, what exactly each of the data point looks like, right? So each digit or each data point is a 16 by 16 image. And here we are showing an example for 6, right? The number 6. It's a grayscale image, as I said. And notice you have like these number values. So basically the numbers will range from -1 to +1, where -1 is for, I think, white and +1 is for black or something like that. So basically anything in between with different intensities is like some shade of gray, essentially, right? And because this is 16 by 16 image, and that's how we have like kind of divided the squares into, right? Like this. And so basically, if you look at it, the dimension or the dimensionality of this problem, because each of the digits is a point, right? It's a data point or it's an observation. So it's like the dimensionality or D of this data is 256, right? And I'm going to have like 256 dimensions throughout. Okay, so if we run my perceptron learning algorithm in this, and the problem could be like categorize two different types of digits, or maybe pick up like, let's say digit 5 and digit 1 and try to classify them correctly and so on, right? The problem could be anything, but if we think about running the PLA for that, my VC dimension is going to be D plus 1, which is around 257. Okay, all that is fine. If you remember, right, from our some earlier lectures, theory tells us roughly how much data would we need if we want to have like that much amount of the VC dimension, right? So roughly speaking, I will have VC times 100. That is going to keep us safe in terms of establishing the very first rule of learning that E in is almost equal to E out, right? So almost 257. So that like the of the order of like 25,000 maybe, right? That is the amount of data we need. Well, if I actually look at the data, I don't have, first of all that data. And let us assume that I actually have only 500 points. Let's say that I'm restricted by 500 points. Now, the issue that comes up here is with 500 points and using this formula, right? With 500 points only, my VC dimension will be 5, or like at least like at most 5, or maybe less. I don't know. Now, because we also need to start, like we first of all need to establish the first step of learning, and for that we need like a smaller VC dimension so that we can get like E in close to E out. But then in terms of learning, I'm not done here. I also need to do something with my second step of learning, which was that E in should be really close to 0, correct? So I have to come up with some idea of getting E in close to 0, because even when I'm trying to get E in close to E out, I need to have certain things, right? So how can we do that? How can we get an E in close to 0 with a smaller VC dimension, right? Because this looks like I will have to throw out some dimensions, I would have to throw out some features, discard them, or something like that. Well, there are ways to deal with that, and one way of doing that is known as feature construction, right? So we can do feature construction, and this is mostly done when we are trying to get a smaller E in and trying to establish the second rule of learning, right, with a smaller DVC, right? And so we can summarize the input into features that are useful for classifying digits. So summarize what we have, basically summarize what we have, or summarize the input into features that are useful. And I'm going to elaborate on what that means, right? That's important, that are useful for classifying digits, or that are useful for the problem at hand. Now, there are two things we will accomplish, right? So the first thing is like useful in terms of like shrinking my VC dimension, first of all, right? Because if my VC dimension is huge, you know that I cannot create that first link and first rule of learning. So that is known, right? So two things that we'll accomplish by doing feature construction is that we will reduce the dimension, and so the VC dimension as well. So reduce the dimension and also the VC dimension significantly, because like then only we can get hold of the first rule of learning, which is E in close to E out, or as close to E out as possible, right? So that is the first thing that we will accomplish by doing this feature construction. And the second thing is that the second thing is like we have to get E in really small. So how do we do that? One way is figure out with a domain expert what really is important for the problem, right? And once you figure out, so what is really important? Figure out. Okay, so what is really important for the problem? So once you figure out what are the essential components with respect to the features that we have, the linear model will solve your problem easily. So that is what we have to do in terms of feature construction. Let me demonstrate what I'm talking about. So for example, for the digits data, let's say my task is to classify digits 1 and 5. Let's say I just discarded everything. Regardless, I still have my dimensions as 256, right? So I have to come up with some new dimensions that would not lose any information, that would be equally useful in terms of getting the correct VC dimension, at least a lower VC dimension, because usually in a problem, I'm given some data. So for example, in this case, let's say I'm given 500 points. I know my VC dimension is going to be around 5. And so I have to do something with the features to come up with those kind of features to ensure both the first step and the second step of learning. Okay. So how about in this case, we have like these pixels or grayscale values, whatever we want to call them. How about we come up with the intensity of those, right? Because like just by looking at this and looking at the two digit types, I can tell that intensity, or like if you imagine the square box, right? And let's say 1 is written here, and again the square box, 5 is written here. And those are divided into these like 16 boxes, right? Of course, I cannot accommodate them. But then if you if within every square box, if you count the blacks, right, the black colored ones, intensity is going to be like the total number of the black boxes will be different for 1 as compared to 5, right? So intensity is different for 1 and it's different for 5. So this is like from my knowledge of the problem, not of the data. I'm not looking at the data, I'm just looking at the problem, because the problem is go and categorize 1 and 5, right? So that's the first one I come up with, which is intensity. So this could be a feature, and this is built upon what I already have. I already have like these values within these small squares, right? So intensity is the first one. The other feature that I can think of is maybe symmetry, right? Let me try rotating like one of these numbers, right? And see how much they change, how much they come back to their same alignment. For example, symmetry can be easily defined using 0. So 0, if you rotate it by a certain degree, right, it usually doesn't really change its kind of orientation in terms of how symmetric it is on both sides, or whatever axis you select. Check the symmetry, it's mostly the same, right? So the second one that I'm thinking of is maybe symmetry, but we have to be extra cautious when using features like these, because symmetry is not like some general definition that came up with. I have to have some sort of process to define it. So maybe at times we have to come up with feature construction such that we need an algorithm to come up with that. So most likely for the symmetry part, we need to write an algorithm that is going to ensure the symmetry for whatever, using the feature information that we have, using those numbers -1, +1, whatever we have, right? So for symmetry, most likely you will come up with an algorithm, and I remember it is in one of the homework problems. And for intensity, you can simply add up the pixel values, and then you can come up with that, right? So like, let's assume we have come up with our own features, and we've decided, okay, these are the two features we will be working with. Next, what we have to do is convert this definition, like which I did define, like intensity and symmetry, into like give it a mathematical form, because eventually you'll have to code it up, right? So give it a mathematical form. Okay, so if you just look at it, like using these 256 dimensions, I have come up with this new definition of features, and I've come down to just 2 features. So what does that tell me about the problem at large? Well, the very first thing that it tells me is that I have accomplished a VC dimension of 3. Well, that's great news, right? That is an excellent news. Why is it an excellent news? That is because if you think about the linear model, it is so powerful because it took care of my very first step of learning, which was like E in coming close to E out, right? It took care of that because it was good in the sense that like the VC dimension is of the order D+1, right? So it took care of that. And then you have to do obviously certain things like we did feature construction in this case to take care of step 2 of learning. So it is powerful in the sense that we can apply the entire learning process for the classification problem, and using some additional things like feature construction in this case, right, to get good results. Okay, so theoretically speaking, right? But now we'll have to look at what we did with the features and how the algorithm actually works on that, right? Because we're just saying theoretically that, okay, all of this is good because we got a lower dimensional data. Okay, so let's look at these new features first of all. And just like a word of caution, we're looking at this. Of course, in practice, you cannot look at the data, but just for teaching purposes, I have to, because we need to discuss what's going on. So let us assume that this is like I define my symmetry and my intensity. So you can tell that 5 has more intensity than 1, and 1 is more symmetric than 5, right? So this is like the data, this is the new data distribution it'll look like, right? Ones will lie in this like blue heap sort of here, and yeah, so because like 1 is more symmetric, and maybe this axis is like symmetry, and this is intensity. So as you can see, the intensity of 5 is more, but symmetry is lower, and it's the other way for 1. And some of the points that we wanted to notice are like, for example, look at this blue point here. This is a 1, obviously, but it lies in that other heap of like 5s. And obviously you can tell because this doesn't look as symmetric, and it does have a higher intensity as compared to other ones, right? Similar to that, somebody, believe it or not, wrote a 5 like this. Well, it is highly symmetric, so obviously it tends to lie in the group of ones, right? And then the intensity is also lower, as you can tell, because it's not really spreading out in that entire square. So the sum of all the values of the grayscale values would have been lower, right? So this is here the feature construction, and we looked at two features, intensity and symmetry. Just so you know, feature is an important, like how do you define it? It's an important property of the input that you think is useful for classification. And useful is especially important. We just saw why. Okay. So as you can see, because I have like these two features, I can visualize my data now, first of all, because I couldn't visualize it earlier like this, at least in terms of like the separation and all. And now I came up with my own definition of intensity and symmetry. You will have to do that as well for every problem that you're looking at, right? So that's how we can like summarize the two new features that we came up with. And now I think we are ready to run the perceptron learning algorithm on this and see what's going on, right? Okay, so we ran the perceptron learning algorithm, and these are the results that we got. First of all, this here is my classifier. So this is my final classifier with the perceptron learning algorithm. And as you can see, it took around 1000 iterations. So these are my iterations. So it took 1000 iterations to achieve that, right? And which is not bad at all. Now, there are these blue curves and these are red curves. So what are these blue curves? Blue curves are nothing but E in, my in sample error that you observe. Now, because data is not linearly separable, we see the erratic behavior. As you can see, it goes up and down, and we're just simply like iterating and getting my E in and plotting it. That's all I'm doing. Now, there is this additional red curve, right, which is E out. And the question that arises is, how did I come up with it, right? Like, what is that way of calculating E out? Well, the trick that was used for this particular experiment is that only 500 points were used for training. So only 500 points were used for training. And then there was a larger data set of around 10,000 points that was left out as a test sample, just so that we can mimic this E in, E out like process. So that's important. Now, another important thing to notice here is that if you look at the way the erratic behavior is going on, E in and E out are in perfect sync with one another, right? In fact, E out is kind of mimicking, I would say, E in, right? And so they are in perfect sync with one another. And why do you think that is happening? Well, that is our theory at work. That is what we did all these weeks, all these previous weeks, and finally we are here. So our theory is at work. My E in is linked to E out, remember? And because we have a VC dimension that is so low, that link is really tight. The link between E in and E out is really tight via the error bar, because my VC dimension is extremely like small. Okay, so having said that, let's look at what my pocket algorithm does. Okay, so here's a comparison, the same data, the same features, two features. And remember, the pocket algorithm is just like keeping track of the lowest E in and just like keeping it. And if it doesn't find a lower one, it just keeps that. So that's what this one is showing. And again, we decided that let's run it for 1000 iterations. Well, that looks kind of okay because it wasn't improving as much. And so we just like stopped there. Well, it's pretty much well behaved as we expected, and it's like keeping the E in. And the classifier might be a little shifted if we look at it, but not as much. Like as you can see in the pocket algorithm, we are like in the PLA, we do have like a greater bunch of like misclassified points because we are just not keeping track of what was our best, right? And so we are just like going on and on. But here we are just like keeping what best I have. Okay, so that was a comparison of the PLA and the pocket algorithm, and this was also showing us like this video was essentially telling us about feature construction. In the next video, I'm going to look at linear regression.